Hey guys, so happy. I can really see that people are joining in. They're ready. You guys are ready this Sunday. I'm so happy for you guys to be here. If you are returning to a Q&A, welcome back. And if you are new to these Q&As, so happy that you can join me and experience what this Q&A and this beautiful community is all about. So before we start answering questions, which I will do very soon in like 2 minutes. You kind of see that countdown here. I wanted to clue you in as to what in the world I'm working on, what I'm doing, and when the next video is coming up. So I really filmed another video that's going to be launching this week. So don't worry, guys. That's definitely coming up. It's going to be on limiting reactants. And now, pretty much what I wanted to let you guys know, and I'm so excited to tell you about, is I started making my own workshops. So I just created a Lewis structure workshop, which is currently on pre-sale, meaning it is half off. So that is how it's designed. It is absolutely everything you need to know. So what a workshop even is, by the way, a workshop is kind of like a pre-recorded tutoring session, but even more in detail. So it's not interrupted, it's really just kind of like, think of it as it's different lessons that I prepared for you guys specifically, and it goes in a specific order for you to fully understand the concept of Lewis structures, whether it be how to draw them, how to state, is it polar, non-polar, figuring out the hybridization, the geometry, the pretty much everything, the formal charges, which one is the best structure. So I have laid out absolutely everything in order. It even comes with my own notes that I've designed for you. They're beautiful, if I must say. So definitely check that out. After this live session, you'll be able to see that in the description box once this video is then posted after the live session. And if you're not on Lewis structures just yet, I would say definitely reserve it. Either way, it is a common topic that I have seen students struggle with. And I understand it's a totally different language, totally different concept. And I'm also now doing more of like study guides. So what study guides or what my notes really entail, think of it as it's a way to just explain every single step of the process. And it's kind of like a guide for you to have. So I just created one for limiting reactants, percent yield, theoretical yield, excess reactants, and all of that. So I would say to definitely check it out. It is at a very, very low price. So if you could think of it as some of them are less than your own Starbucks drink. So that's kind of what I wanted it to be. I wanted it to be affordable for you guys. And yeah, so definitely check that out. I also, if you guys aren't a part of my community, what I mean by that is I have a sign up form that you'll be able to see at the end of this live stream. So in the description box, and it's also in every single one of my videos. I give you guys a free formula sheet. I found that is extremely helpful. I wish I personally had that when I was doing chemistry, when I was in, my classes. So I wanted to provide that resource for you guys. So if you sign up for that email, if you sign up for that form, you'll be able to receive a formula sheet with everything that you possibly will see in the first half of chemistry. So, and it's already in the description box. So yeah. All right. Now, and then let's see who we got. I see so many people already coming in. This is awesome. Genesis, hello. I'm so happy you're here. I hope I'm not butchering your name. Minha, thank you so much for joining me. Hello. And who else do we have? Tatiana. We have Abraham is saying what's up. And all right. So we really have our questions rolling in. I'm going to start answering some questions. Genesis, I'm going to start with yours. And just to kind of let you guys all know, to move this along perfectly and like smoothly, I would say if you have a specific question, like let's say Genesis has a perfect example here where she actually put the numbers and what they're asking. That helps me so much to just be able to answer every single question as quickly as possible. Okay, so that's something that I would definitely recommend. If you have a specific question, put it in the chat. If not, then I'll do my best to find a specific question for you. All right, so let's start off with Genesis's question, and she states, for a problem like this, if a patient's blood pressure is, and let me start writing down everything that we got. So all of our givens in this question. So if the blood pressure is 115 over 55 millimeters mercury, what is the atmospheres? What is it in atmospheres? And then would I have to convert millimeters mercury to atmospheres using 760? Yes. So you would. This specifically, since it's saying 115 over 55, what would it be basically in atmospheres? You would have to convert that. So what you're stating is to go from millimeters mercury, you're going to use 760 millimeters mercury is equal to 1 atmosphere. So using that conversion factor, it's really all you would do in this case. So what I would do, and I just want to see, since I remember Genesis, that's right, you're taking a nursing class, so this is definitely a nursing question. If a patient's blood pressure is over that, so that's really all you're necessarily going to do. Is this is essentially going to be what we're dividing. And then I believe that they also, since they want it in atmospheres, yeah, I'm going to divide these two values since it is saying over that amount. So 115 divided by that 55, 2.0909. This is still in millimeters mercury. And then now, actually, I believe that, did they want it? I'm assuming they just said, what is it in atmospheres, just because it is a blood pressure question. Because what I was considering doing in the very beginning was leaving, actually, I might just do that, leaving this all divided by atmospheres because you want it over a specific pressure. So that's what I would do. Because I want to cancel out our millimeters mercury, I'm going to align them so they can, and putting that across from each other. And then since we wanted this in a specific atmospheres, but they are stating, you know what, hold on. Let me just double check this question. Since it is a nursing questions, I know they word it differently. If a patient's blood pressure is at over 55 millimeters mercury, it is specifically the 55 meters mercury. Yeah, then you would still want it to be over some sort of pressure. So that's all you would do, is you'd multiply by your conversion factor of that 760 millimeters mercury. And then let's see what we get with that. So multiplying those two. And then we just really change this to atmospheres. So here. That's how much I would get. I would change the sig fig amount to 2, since that was our lowest sig fig count. So I'll move over the decimal place 1, 2, 3. So 1.589 times 10 to the, we move this over 3 times, atmospheres, and then I'll round to just 5. I'll round that up. So 1.6 times 10 to the 3rd atmospheres. Yes, all you had to do was change using that conversion factor, and that was it. You also asked another question. Can we go over oxidation and reduction problems? Absolutely. Let me grab a question real quick. Just looking at that. Let's see. Oxidation. Okay. So oxidation and reduction is going to go back to oxidation numbers, and I'll specialize on what I'm talking about there. All right, let's see. Okay, so let's say if I were to have, and actually even before getting into that specifically, let me talk about oxidation numbers just because we have to know them. So first things first with our oxidation numbers is whenever something is just one element and it's like by itself or in a solid state, for example, if we had Na or sodium just by itself in its solid state, the oxidation number would then be 0. And then, by the way, what an oxidation number is designed for, or what it's used for, it's just to kind of see how many electrons are being transferred or they're being gained or lost in this overall chemical reaction. That's kind of why we need them. I don't want you to think that it's the actual charge of the element itself, even though it's going to seem that way. It's only designed to look at how many electrons are being gained or lost. So continuing with that concept, the other one would be oxygen. So oxygen oxygen would have a -2 oxidation number, and then hydrogen would have a +1, and all of your halogens, so chlorine, iodine, bromine, all of those would have a -1 oxidation number. Then we'll go into diatomic atoms. So anything that's diatomic just states that it exists in two. So di meaning two. Think of it as, how I remember it personally, is Chon and your halogens. So this is specifically when it's a type of gas, by the way. So let's say what I mean by diatomic is this would have been C2 and H2 and O2, N2, and I think you get the point, Cl2, and so on. So everything exists in two or in pairs. That would have an oxidation number of 0. Okay, one more thing. So the next thing is, let's say if it is an element by itself, but it already has a charge. So let's say if it's iron with a 3+ charge, then our oxidation number would be that 3+. So I don't necessarily want you to confuse you with thinking it is the charge of it. Just think of it as its only purpose is to see how many electrons are being transferred. Okay, so now that we have that understanding, let's apply it. And I'll give you a question just showing you which one is being oxidized, which one's being reduced. But to even figure that out, you need the oxidation numbers. So let's say if we had hydrogen peroxide, and here, I'll keep writing all of our different ones. And let me continue writing this out. We will use that table that I just created and talked about. So that is extremely important. And then how I want you to, or how this is really designed to be used, is you're going to start from the top and then work your way down. So typically, we're gonna look at, if there's oxygen, then instantly start with the oxygen and put that it's a -2 oxidation number. If you see hydrogen, put a +1. If you see a halogen, put a -1, and so on. You'll see how this is really designed. So like, let's say for hydrogen and oxygen, since we know both of them already, we don't have to do any math really, or even, second guess ourselves and not even knowing which one's which, meaning we know that oxygen for sure has a -2 oxidation number, and hydrogen for sure is a +1. So that's it. That's all we can say. And then we'll move on. And then, however, here with Mn or manganese, we don't know what that oxidation number is. So we have to figure it out using what we know. So since we know the oxidation number of oxygen, then that's what I'm going to start with. So I'll start with -2, since that's our oxidation of oxygen. Then from there are 4 oxygens. So I'm going to multiply by -2. So 4 times -2 would give us a -8. And all I want you to think about with that step that I just did was, since there are 4 oxygens, each have a -2 oxidation number. If we were to add all these together, that's where I get that -8 oxidation number, okay? And then from there, here's where we're going to get a little bit into algebra, very, very small, but this would have been -8 is going to equal our overall charge of the entire compound. So since the entire compound is a -1, that's what the sum of both of our oxidation numbers will then equal. So I don't know what manganese is with the oxidation number just automatically. So by doing this, by setting up this question, I'm going to state that it's X, and then we just found that the oxidation number for oxygen is -8. And then it all equals -1, solve for X, add over the 8. So then this gives us 7. So then this is a +7 oxidation number. Okay, I'm going to keep going. So there's another one. Now this was another case that we saw. If it's a single element with a charge, then that's our oxidation number, the 2+. And then lastly, O2, it's a type of diatomic atom. It is a gas. So right then and there, that's 0. Okay, so now that we got that down, let me go ahead and erase all this. So this is all we're looking at, by the way. All of these that I just have on the screen are oxidation numbers. I'm going to go back to just clarify something. And that -8 is not the oxidation number of one oxygen. We're only looking at the oxidation number of one oxygen. So that's why I erased it and I left it as -2. That -8 was only designed there to help me figure out what manganese or Mn's oxidation number was. All right. So typically hydrogen is never going to be reduced or oxidized because it doesn't change its oxidation number. So that's something that I typically never look at, but I'll show you how I instantly know what's being oxidized, what's being reduced. So with oxidation, I want you to think it's becoming more positive. So let's first just look at which oxidation number went up or became more positive. So in this case, what happened was our oxygen. So our oxygen went a little bit more positive because it then became 0. So it went from -2 to then 0. So this is our oxidation process. And like I said, I just want you to think oxidation is becoming more positive. Now, what's really occurring here is oxidation is a loss of electrons. So think of it this way. You become more positive when you lose negative people in your life, right? So, or you lose any negativity. Any negativity that you lose, you become more positive. That's oxidation. Now with reduction, you are gaining electrons. So electrons are negatively charged. So as you surround yourself with negativity, you become more negative. So that's one way to think of it. So then now we're going to look at that and see which element or oxidation number became more negative or really got reduced. And then we'll look at manganese. It went from a +7 to a +2. And right then and there, that's what's being reduced. So that would be reduction, because it's becoming more negative because we're gaining electrons. And cool. That's a great way to remember. Thank you. You're welcome. Genesis, was that all that you needed with this specific question? Let me know. Did you also need to do half reactions? Definitely let me know. And then I'll move on to the next question. Let's see. So I'll keep going and just show you the half reactions real quick, just to be thorough, and then I'll move on to the next question. Okay, so with our half reactions real quick, oxidation, just what half reactions are, by the way, it's just showing the process of oxidation, and then separately with whatever elements are happening with oxidation. And then next it's reduction, just seeing what compounds or what's changing in reduction. So meaning if we have our oxidation here, what's being oxidized? Well, we know for sure H2O2 is the only thing that's occurring, and this is going to O2 gas. So that's the whole process of oxidation just for this specific type. And then for reduction, we're using the manganese. So our manganese is really what's being reduced, but I'll write this out. So this would be our reduction process. And then from there, the last thing or a couple things I'm going to do is figure out how many electrons are being transferred for everything. So let's say for here. Let's go back to this one. So let's say for our manganese, we see that it goes from +2 to +7 to +2. So what we're going to do there is just subtract. I want you to think of it as its final minus the initial. So 2 minus that 7 would give us 5. And it's fine that it's negative. Electrons are negative. So that would just mean that there were 5 electrons transferred. And where I'm going to put that for reductions, for the reduction half reaction, think of it as reduction reactants. So you place the electrons on the reactants for the reduction half reaction. Whew. Okay, so that's where you're going to put your 5 electrons, is just attached to the reactant side. And then for oxidation, it's the opposite. You're going to add that to the product side. So looking at how many electrons are then being transferred there, let's go back. Well, we see that we would have done 0 minus a -2, which gives us a 2, or +2 really. So 2 in this case. So then, okay, I'll add 2 electrons, and that would be your half reactions. Lastly, if we were looking at what's our reducing and what are our oxidizing agents in general, remember your reducing agent is actually what's being oxidized. So reducing agent in this case would be the manganese or manganate in this case. So that would have been your reducing agent. Where we're taking this, just because that is being, it's whatever is being oxidized. That's our oxidizing agent. So a reducing agent is whatever's being oxidized. We said that our hydrogen peroxide, there we go. Hydrogen peroxide would be our reducing agent because it's being oxidized in this case. And then our oxidizing agent is going to be the opposite. It's basically whatever's being reduced. So this would be our oxidizing agent. And how I want you to think of this, I want you to personally think of this, is the reason why we're never going to use the products as let's say any sort of agent, any sort of reducing or oxidizing agent, is because it's already done. Like, think of it as that agent, that oxidizing or reducing agent, has to do the work. So it must have been in the very beginning. It must have been in the reactants. So your oxidizing agents or reducing agents are always going to be one of your reactants. All right. So that's really everything with oxidation and reduction processes. Yeah. So I'm going to move on to another question, and let's see what we got. Tatiana states, I'm struggling with representing the structure of organic compounds and drawing the skeletal structures. Okay, so I'll show you a little bit what I'm doing right now, guys. You're probably going to see this later on. It's organic chemistry. So if you are deciding to continue with chemistry, you will see organic chemistry here. And you're welcome, Genesis. Happy to help. Okay. Let's see what I can do here. So I'm going to start off with just something a little bit simpler, and then I'll start to draw different types of structures, Tatiana. So like, let's say if they were to give you this sort of, alkane, right? Or this sort of compound structure. So what I want you to think of this as, and by the way, what I stated, alkanes, remember, are just single bonded carbon chains. And how I'm going to represent this, how many carbons do we have? Well, there's 1, 2, 3, and 4. So since there are 4 carbons, my trick for you when drawing these skeletal structures is to always draw one less. And I'll explain what I mean. So kind of watching me draw this, I'm going to count 1, 2, 3, and be done. Because every single point, remember, counts as a carbon. So in this sense, we just drew 1, 2, 3, and 4. And that trick will always work, by the way. So as long as you like mentally or, say it out loud, thinking of it as, okay, I'm going to draw 1, 2, and 3 lines per se, that is always going to give us 1 extra carbon. So this is actually the skeletal structure, and I'll prove it to you. I'll show you that since every single point is a carbon, then from there, we have to have hydrogen that are attached. So sadly, our hydrogen will be not shown in our skeletal structures. It's just a way to draw it nicer and less kind of crammed and packed. So there are 3 hydrogens on the ends, and there's always going to be 3 hydrogens on the ends, because remember, this is going back to Lewis structures. Carbon wants to be content. It wants to be happy. So from there, that's pretty much what we have to do. We have to make sure that carbon has a full octet, meaning 4 different bonds. So it's going to mirror itself on the ends. And that's also going to be the case. So that was this 4th carbon. And then in the middle, we'll see, okay, this is going to be attached to 2 hydrogen. So that works out. I'm going to draw a couple a little bit. I'm going to like increase the difficulty level just by a tad bit, just so we're understanding this. So let's say if I were to start to, to draw, let's say if I were to add some substituents. So let me see what I want to throw. Okay. CH2, CH3. I'll connect this other one, CH and CH2. This would be a CH2. 2CH. That's fine. Okay, there's 1, and then I'll start with that. Okay, so let's say if we had, and actually I'm going to do 1 methyl group, CH3. Okay, I'm done. So let's say if we have something like this, and we're trying to draw this in the skeletal structure. What I personally would do first is This goes back to kind of like naming alkanes. And remember, doing naming alkanes or nomenclature, you always look for the longest carbon chain. And then from there, you're going to figure out what your substituents are, and we'll name that all. And, there's a long process for this. But the main thing that I want you to look at is go ahead and count your carbon chain and see how many carbons there are, because that's going to help you draw it. So that's what I would do first. I would count what's my main carbon chain. So I'm just going to look straight across and see that this is 1, 2, 3, 4, and 5. And I don't care about naming at this very second, just focused on how to draw this. So that's what I'm going to start with. I oftentimes, when I'm teaching OChem, I oftentimes think of this as like the longest chain, or the main carbon chain, is like the body of this structure. And then your substituents, which are the ones that are kind of sticking out, those are your arms or legs or some sort of limbs that are just sticking out of the body. And then you'll note that that's what I'm going to draw right now, is I'm going to draw the body of the skeletal structure. So since there are 5, I'm going to go back 5 carbons. I'm going to go back to my trick that I taught you, that I'm actually going to draw 4 carbons or 4 lines. So let's do this. 1, 2, 3, and 4. And believe it or not, that is 5 carbons at every single end. 1, 2, 3, 4, and 5. So that's just the body of it, or the main carbon chain. Now I'm going to come back and I'm going to renumber this and see, okay, where are all of my substituents in this structure? So we have, I'm going to circle it, we have a methyl group. Remember, CH3 is just a methyl group, and that's going to be sticking out at 2. So what a methyl group, or CH3, really is, it's just a line. It's just a line that we're going to draw, because on top we actually have that carbon, and remember, we have 3 different hydrogens sticking out. So that's really where it would go, but I don't have to draw that. With the skeletal structure, it's just like a nice way to not draw all of the elements. And then I'm going to keep going, and I'll see, okay, what about this other substituent? Well, that's sticking out at 3, so I have to place that at 3, and this has 2 carbons. So how I'll draw this, and that actually should have been a 3 at the end, CH3. So it should have been CH2, CH3. How I'll draw this is I just need 2 different carbons. So then this is essentially stating, this is actually an ethyl group. Remember, ethyl is 2 carbons. So then this is a carbon right there that has 2 different hydrogens, and I'll show you in a second. And then this is our N portion, which has that CH3. So that's how you would really process this and design this, where I want you to draw the body of the structure first, and then using that trick. So remember, when I'm drawing this, it's always like one less line, or one less carbon that you're thinking. So instead of actually counting out 5, I counted out 1, 2, 3, and 4. And then that always gives us 1 extra carbon. So that's something that I recommend. And then from there, if you have so many substituents, then start to add that to the body of every single, wherever that carbon is supposed to be. So like in this sense, our substituent our methyl group was supposed to be on 2. So that's why I just placed a line, which is just a methyl group. And then on 3, we saw there was an ethyl group, making it just 2 carbons. So that's why I had to draw exactly 1 and 2 carbons. This was our CH2, and then this was our CH3. So always at the end, there are CH3s. Whenever we just have really 2 lines here, they are CH2s, because what's missing that carbon requires 2 more bonds, so there has to be 2 hydrogens. So that's how I personally want you to think of it, Tatiana. Hope that's making sense and you can, understand those tricks. And then I have another question. Okay. So let's see what I got. Min is stating, please review molarity and how to find it. Okay. So going back to molarity, let's just remember what the formula is. So molarity, or capital M, is going to be the moles of our solute divided by the liters of our solution. And then the main thing to kind of note with these types of questions, it is very important to know, what is your solute, what is your solution, just to kind of go back to solutions and what everything is. So let's say if we were making, I typically always use this example, if we were making iced tea and specifically sweetened tea. So with sweetened tea, let's say if I were to put sugar, okay, and this was my tea. So the liquid was my tea. So this little sugar portion is what is being dissolved. Whatever is being dissolved is your solute. So it's typically some sort of solid, by the way. And then your solvent, or the tea in this case, some sort of liquid, is whatever is doing that dissolving. So your solute is being dissolved or broken apart, and then your solvent is doing that dissolving. So it's what's causing the solute to dissolve. So, and then our entire solution would be our solute plus our solvent. Okay, so I have seen some questions where they don't give you the solution and they just give you the solvent and then the solute, and they expect you to know that a solution is equal to solute plus solvent. So be warned with that. And then I'll also give you another example as to how to find molarity. Let me grab a question real quick using molarity. Let me see if I can find one quickly. So here we go. Okay. Just pulling from all the lists of different examples that I have for you guys. Let's see what I can find. Into moles, that's something different. I want one that actually includes, there we go. Okay. So let's say if we had to find the molarity. So what is the molarity? And we'll go back to the formula in a second. So what is the molarity of a solution with 15.0 grams of NaOH per 500.0 milliliters of our solution? Okay. So since we want our molarity, we are finding that overall equation. So molarity is moles of our solute divided by the liters of our solution. And then let's go ahead and just write our given and then see what we have to convert. So what was given in this initial question was we have 15 grams of NaOH. Okay, so 15 grams of NaOH. And then we're also given 500 milliliters of our solution. So that already is our solution. So how nice. Okay. So the only thing that we can possibly see because of the information provided was that since we're going from grams of NaOH, that's going to be our solute. So that is already stated. There's nothing else that it tells us. So right then and there, what I'm going to do first is going to be a 3-part question where, since I want the moles of my solute first, I have to then change grams to then moles of NaOH. So that will be my first step, going from grams of NaOH to then moles of NaOH. And then remember how we do that, how we go from grams to moles or moles to grams, is by using the molar mass of that compound. So molar mass, just going back to the individual masses using our periodic table, and that's exactly what I'm going to do, the sum of our individual masses. So let me find the molar mass of NaOH. So Na is roughly 23, and then oxygen is 16, hydrogen is 1. And I rounded, guys, this is just kind of the ones that I always know and they always use. So I'll add everything together. Okay, so we'll get 23 really plus 17. Then that gives us 40. So in total, we get 40 grams per mole. I'm just adding the individual masses and trying to get the molarity. Trying to get the molar mass. And then from there, I'm going to use the 15 grams initially that they gave us on our given. Change this to moles. So placing the 40 grams of NaOH on the bottom, we want the grams and grams to cancel. That's why I placed them across from each other. And also we want to find moles. That's why it has to be on top. So real quick, for everybody who's watching this and who is struggling with, let's say, moles or, conversion factors, stoichiometry, what I just did here, I wanted to go from grams of NaOH to then moles of NaOH. That's why I place the grams on the bottom so they can automatically cancel. We always have to place them across from each other so they can cancel, and then we can move on and finally get our desired unit, which was moles of NaOH. Your desired unit, or whatever you're finding, will be left on top, and that's how you know you're done. That's how you know you got to what you wanted. So then from here, let's go ahead and divide. So let's see, 15 divided by that 40 will give us, there we go, 0, and let me make sure, there we go, 0.375 moles of NaOH. Okay, so then now, next thing, now that I have my moles of my solute, I need the liters of my solution. But sadly, they didn't give me that. They didn't give me the liters, but instead they gave me the milliliters. So that's our second step, is to convert from milliliters to liters. And then remember, we will be using the metric system for that. So part 2 would be going from milliliters to liters of our solution, starting with that 500. So they give us 500.0 milliliters of our solution, and I'll place the milliliters and milliliters across from each other so they can cancel, and the liters on top, since that's what we're finding. So there's 2 ways to do this oftentimes, and this is whatever you prefer personally. So I've taught the metric system, if you've seen my previous videos, as this is 10 to the negative third for our base unit, which is liters, and the different unit, which is the milliliters, is 1. You can do it that way. You could also do 1,000 milliliters for every 1 liter. They are both going to give you the same answer. So whatever you prefer there. And let's see, this is really just going to, since we're dividing by 1,000, it's just going to move the decimal place 3. So by 3. So 1, 2, and 3, this would be 0.5 liters. And then from there, this would also give us the same exact thing. Okay, so now that we have our solution in liters, the last step is to divide them. So we found the moles in part 1. We found the liters in part 2. Part 3 is just to divide our moles divided by our liters. So for part 3, since we're looking for molarity, we said it's the moles divided by our liters, specifically the moles of our solute divided by the liters of our solution. And that's exactly what I'm going to do. We found previously that the moles, so I'm taking this number, the moles was 0.375 moles of NaOH. And then we just found here our liters was 0.5 liters of our solution. So then this is our solution. So I'll divide, and that gives me my molarity, and we're finally done. So 0.5, this is 0.75. You could either write this as moles per liter. I'd say the most common way, and I want you to get used to it writing this way, is putting a capital M. They mean the exact same thing. Capital M just means molarity. Yes, it does have to be capital. It does have to be a capital M. If you put a lowercase m, you will be marked wrong, just because lowercase m can mean meters. It could also mean something known as molality. There's just several different things with a small m. Why didn't they choose a different letter? No idea. But I didn't make this stuff up. So that's how, there you go. You have molarity. I'm going to move on to the next question. Hello, Shelly. Welcome. Hi, Melissa. Moles and 5-step problems. Okay. Let me see what I can find. So going over moles, let's say, let me grab a stoichiometry question and see what I can find. 5-step questions. Don't know if I automatically have a 5-step question. I can definitely put a multiple question here. Let's see. I can do I'll do a stoichiometry question looking at, let's say this one here. Let me write it all out. Let me figure out which one I even want to do. What mass of that? I kind of want to do that one's perfect. Okay, that one's perfect. So here, I'm going to put a unbalanced equation. We will have to balance it real quick. And then I'll put our question. Here we go. So how many molecules? So this is one that's going to require all of the conversion factors. That's what I figured you needed. Of oxygen. So many molecules of oxygen are required to react with 174 grams of carbon monoxide or CO. Okay. So before even looking into the question, I'm just going to make sure, is this balanced? It's not. So I'm going to balance out this equation. So for those needing balancing help, I'm going to do that right now. So for balancing equations, all I'm going to do right now is just write out each individual element and how many elements there are, specifically on the reactants and then on the product side. So in this case, our carbon only has 1. Oxygen, however, has 1 plus that 2, so it really has 3. And then on the product side, carbon has 1, and there's only 2 oxygen. So the only thing that's not balanced is going to be our oxygen. So whenever we have that kind of like strange case where one is odd and the other one's even, and you're not really sure how to go about this, I like to change it to 4 and see if I could even change it to that. Meaning I like to kind of go back to the one that's odd and see, can I change that to a even number? So I'll put a 2 in front of that CO to change it to be 4. So, and how I did that, how I mentally thought about that was just, if I were to put a 2 here, it really is going to distribute to both of these elements, and there's going to be 2 oxygen with this CO plus this other 2 oxygen, so that's where I get 4. And then with carbon, that would give us 2. So, okay, we're not balanced just yet, but we're almost there. So then to balance out the carbon on the product side, all I have to do is put a 2, and once again, this will distribute, and we'll have 2, and then now 2 times this 2 for O2 or oxygen, then that would give us 4. So right then and there, boom, we're balanced. So that's what I personally like to think of whenever we have an odd amount of oxygen. Just see if you can make it an even number. I start with going to 4. If that doesn't work, then I move up to 6, but typically it normally works. So, okay, now that that is complete and that is happy, let's erase this part and then I'll leave the balanced equation. And we'll identify, what are we given, what are we finding, and we'll build a plan and see what in the world do we do. So let's go ahead and start with just figuring out, what did they give us? Okay, so now we have our balanced equation, and we are given just the 174 grams of carbon monoxide. So that's the only information that I'm really provided with. All right, so and why this is so important, by the way, you're going to see very soon that the given is where you start. It's always where you start. And then whatever you're finding is where you end. And I'll point out every single little part of this, but that's going to be the easiest way to look at it, is your given will always tell you, what do I start with? And then whatever you're finding, which we'll see in a second, is going to tell us, where are we going to stop? Where are we going to end? And once you reach that, whatever you're finding, in this case, it's going to be the molecules of oxygen. So molecules of oxygen, and beware of this, oxygen is really O2, because they give us that actual equation. And then not only that, oxygen is a type of diatomic atom. Diatomic meaning it exists in 2 or in pairs, so it has to be O2. It's not just O, it's O2. Okay, so now that we have that, let's plan this out. So what they're telling us, they're stating that we have to start with grams of carbon monoxide regardless, okay? And then we're somehow, some way trying to get to a completely different compound, O2. So since I'm trying to change the compound altogether, I know that I have to use a mole to mole ratio at some point. So if you're not sure, I think this is the trickiest part personally with stoichiometry, is where do I go next? What do I do next? So the first thing, if you're not sure where to even start with moles. Seriously, everything is equal to moles. So that's what I want you to think of here. The first thing to just start off with, we are given our grams of carbon monoxide. Instantly change that to moles of carbon monoxide. And then remember, and how we're going to do that with our first conversion factor, grams to moles or moles to grams, is by using the molar mass of carbon monoxide. And then I'm going to keep going. And now that we have moles of carbon monoxide, then we have to change the compound again. Or actually, we haven't changed the compound yet. So we have to change the compound now, because we're trying to get to moles of O2, or we're trying to get to O2. So this is where, now that I have the moles of carbon monoxide, or CO, I'm allowed to change this to then moles of O2, because I couldn't have just gone from grams of, come on, let's see if my pointer works. There we go. I couldn't have just gone from grams of CO and then magically, make my way to moles of a completely different compound. Doesn't work that way. We need something to connect us with that. So then that's why we instantly have to go from grams of carbon monoxide to then moles of the same compound. Now that we've got that in moles, we'll continue using a mole-to-mole ratio going to moles of O2. So that's going to be our second conversion factor, which is going to be our mole-to-mole ratio using that balanced equation. That's why we needed it. And then now that we have that, we have our O2. We have the proper compound that we're trying to figure out, that we're trying to find, right? We stated that here, but we don't have the proper unit. We're in moles, we need molecules. Our final step, whenever we see the molecules, should clue us in and tell us Avogadro's number. That's what we're going to use to figure out, or to really use as our conversion factor. So Avogadro's number, and I know, Shelly, I think you definitely know this part, right? With our, the moles, particles, atoms, formula units, all of those go with Avogadro's number. That should be your clue instantly that you have to use that number. So let's put this all together now. Starting with our given, because that's always where we start with. Then from there, I'm going to put that first conversion factor that we said was molar mass. So just to help you align the units and everything together, we have to put the grams across from each other so they can cancel. So that's why I'm going to put grams and grams across from each other. And then what allows us, what's our next step? What are we trying to get to? We're trying to get to moles of CO using this first conversion factor that we just said. So then before, moving on, let me go ahead and figure out what the molar mass of carbon monoxide is. So carbon has a mass of roughly 12, and then oxygen has 16. So adding those together, we'll get 28. So, okay, 28 grams per mole. And then with molar mass, you're always going to have 1 mole, and then the mass, or the actual number that's changing, is the grams, because that's going to be the molar mass of that specific compound. So, okay, that's what we have so far. And then now what you'll notice is our grams and grams would then cancel of carbon monoxide. And then now we're here. We're at moles of CO, or carbon monoxide. So we're at this step right here. Okay. So then our next part is to change this to moles of O2. I'll once again align the moles. Let me not put that in blue. I'll once again align the moles of carbon monoxide across from each other. And then on top, I'll put moles of O2, because that's what we're trying to find. We're trying to find the compound of O2. And then where I'm going to pull these numbers from is from our balanced equation. So going back to our balanced equation, in purple, I'll kind of circle and highlight where everything is. So where this is the numbers, or the coefficients in front, or what we're looking at. If there is no number, then we're just going to state it's 1. Okay, so everything in purple are your different moles. Now, since we're going from moles of carbon monoxide to moles of O2, what I'm going to use is that 2 moles of carbon monoxide. So 2 moles of carbon monoxide is then equal to, and let's remove that, is then equal to, 1 mole of O2. And I'll show you that again, but I'm just taking these numbers, these coefficients. That's where I use my mole-to-mole ratio. So we said there's 1 mole for O2 and 2 moles of carbon monoxide. Okay, now let's keep canceling stuff. So moles of CO cancel. We're now at moles of O2. One last step. We're at this third step finally, where we want to change this to molecules of O2. So I'm going to keep going and put the moles of O2 on the bottom. And lastly, since we're finding molecules, that's what's going to be placed on top. So whatever we're finding is going to be on top. Okay, now we'll use Avogadro's number, which is 6.022 times 10 to the 23rd. That number goes with our molecules, and it equals 1 mole. So then from there, our moles and our moles would then cancel, and we're left with molecules. So before I multiply everything out, I just want to re-highlight and really, really drive this in where we started with our given, which was our grams of CO. And then where did we end up with? We ended with whatever we're finding. So our molecules of O2. So that's how you know where to stop, and that's how you know you did the question right. And that's honestly why I always, tell my students to write, what's the given? What are you finding? It's because a lot of times you get nervous on your exam or your quiz or really anything, and you're like, what am I finding again? What am I doing? I don't know where to stop. I don't know if I should continue. And at least that finding portion is telling you this is where you stop. This is where you know you did the question right. And then from there, you're going to keep aligning your units across from each other, just canceling everything out. Moving on to like every single possible unit until you get to what you're actually finding, which was molecules in this sense. Hope that's starting to kind of make sense how we're piecing everything together. And then I'm just going to multiply straight across. So multiplying the 174 times 6.022, to the 23rd, divided by 28 times that too. And let's see what that gives us. So this gives us 1.87 times 10 to the 24th. Let me move this over. And then this is going to be molecules of O2. Okay, of O2. And then that essentially would be it. Let me double check my sig fig count. We started with only 3 sig figs, the 174. So yep, that would be our answer. Okay, so that was really stoichiometry. So anyone who also had a stoichiometry question, that should have explained a lot of it. I'm going to move on to another question. Let me erase all of this and give myself some space. And then as I kind of do this, let's see what else I got. Okay. I'm so sorry if I butcher you guys' names. I never mean to. Let's see. I have Shavlita. Hey, can you discuss more about molecular and empirical formulas? Absolutely. So talking now about empirical and molecular formulas, let me grab a question real quick. So molecular. And you know what? I have a whole list of them. So with this, this is a tiny bit of stoichiometry, I would say, but it's really just going from grams to moles and knowing how to do that. And with empirical and molecular formulas, there's a lot of steps, which I'm sure you've already seen before. Oh, where is it? Here we go. There's a lot of steps to every single question. And let me find one for you. There we go. I'll start off with something that is empirical, and I'll see if I can find one that's molecular. I'm just looking through all of my examples that I have in my huge packet. A little too many of them contains that. Let's see. I don't like that one. 1 second. Let me see what I can find. There we go. There it is. Okay. So let's say if we had a question that's asking for our molecular formula. And to figure out what our molecular formula is, we have to figure out what our empirical formula is first. So that's what we're going to do. Let's say if you're given that some compound or sample has 74.02 grams of carbon, and we also are told that we have 8.710 grams of hydrogen and 17.27 grams of nitrogen. All right, so we're given all that. And they're also going to tell us, and they have to tell us, that our sample has a molar mass of 162.3. Let me erase that part. 162.3 grams per mole. And they're asking us, what is the molecular formula? Okay, so I'm first just going to start with changing everything to moles. That's going to be step 1. Now, let's say if this wasn't provided in grams, I've oftentimes seen this as a percentage. You would literally change your percentage. Like, let's say if this was initially a percent, then all you have to do is change it to grams by not using any math whatsoever, just instantly swapping that out and putting a grams, okay? So when it is out of 100, you are able to do that. They typically are out of 100. So now that this is already in grams, I'm just going to convert this to moles using the molar mass of every single element. So I'll use the molar mass of carbon, which is just 12, divide that, and then per every 1 mole of carbon. And then from here, after I divide that, our grams and grams would cancel. We're at moles of carbon. This would be 6.163 moles of carbon. We'll do the same thing for everything. So every single element, we have to change it to moles. And then that would be 8.710 grams. So hydrogen has really 1 typically. I'll be a little bit more exact with this one. It would be 1.01 grams of hydrogen and then 1 mole of hydrogen on top. Grams and grams would cancel. We're at 8.624 moles of hydrogen. And then lastly, we'll do nitrogen. So just dividing this by the molar mass, 14.01 grams of nitrogen per every 1 mole of nitrogen. That would give us 1.233 moles of nitrogen. Okay. So first up, if it's a percentage, change it to grams. Then from there, change your grams to moles of every single element. Now, the next step is to divide by the smallest amount of moles. So our smallest amount of moles would then be the nitrogen. So that's the smallest amount. I'm going to literally divide every single one of these values by the smallest amount of moles. And then let's see what that would give us. So what this gives us, the first one would be 4.998, which we are allowed to round up to 5. And then next, our hydrogen, this would be 6.994, still allowed to round that up to 7. And then the next one would just be 1. So, okay. Now, what this is going to tell us is these are our coefficients of our empirical formula. So carbon is going to have a subscript of 5, and then 7, okay, that's going to go with hydrogen, and nitrogen would just have 1. That's our empirical formula. An empirical formula, I want you to think of it as like an educated guess. Like we have an idea as to how many carbon, hydrogen, and nitrogen are in that sample, but we're not sure. But now our molecular formula is the exact formula. Like it's exactly how many carbon, hydrogen, nitrogen, however many elements there are in that sample. Okay. So then from here, what we're going to do to figure out what our molecular formula is now is I like to think of it as, and I'll show you my little trick for you. And actually, even before doing so, let's just figure out what the empirical formula's molar mass is, and then we'll continue with the steps. So with our empirical formula's mass, let's just calculate this. There are 5 carbons, so 5 times 12, and then H would be 7 times 1.01, and this would be 0.1, sorry, 0.1. And then nitrogen would be 1 times 14 point, let me erase that, 14.01. All right, we would add everything up. So make sure to multiply all of these, giving us 60.05, 7.07, 14.01, and we would add everything together, giving us 81.17 grams per mole. That is the molar mass of our empirical formula. And remember, they provided us with a molar mass of the entire sample. Whatever they're giving you, that's the molar mass of your molecular formula. If they don't provide you with the molecular formula's molar mass, there is no way to figure out what the molecular formula is. That's something else that I want to mention to you guys. I've oftentimes seen that on a multiple choice question. I've seen that they ask you for what's the molecular formula, and one of the options in a multiple choice question is going, and they don't give you the molar mass, I'm sorry. They don't give you the molar mass of the molecular formula. And one of the multiple choice questions is going to say not enough information. It's that one. So beware of that. I have seen that as a trick question. So yeah, I don't know why they always like to be tricky. Now, I'm going to keep going with this, and we found our empirical formula's molar mass. We have the molar mass of our molecular formula. So let's put it all together. We're going to divide now our molecular formula's molar mass divided by our empirical empirical molar mass, empirical formula is molar mass, and then we'll get some sort of number. And then how you remember this, by the way, I have a video on this as well, but how you remember this is don't forget about me. So molecular molar mass divided by empirical, don't forget about me. That's just a quick way to remember it. And then I'll place everything that we got. So we're given our molecular formula mass, and then this is 162.3 grams per mole, all divided by our empirical molar mass, which is 81.13 grams per mole. And then from there, we divide those two values. This is going to equal 2. This value 2, we're going to use that to figure out our molecular formula. So I'm going to go back to the empirical formula and multiply all of our subscripts by that 2 that we just found. So multiplying this by 2, multiplying this by 2, and let's see what we get. So our molecular formula now would be C10H14 N2. So that would be our molecular formula. And previously, without these 2's, that would be our empirical formula. So that's how you really look at it. I'm going to place in the chat right now the videos that I have steps on, and it's all written out. So definitely check that out. I placed the molecular formula one. To better understand these, it's really just remembering all the little steps, and it just becomes easy afterwards after you've practiced enough. But really, it's just a bunch of steps. I know it's not as much math as I guess you would think with some of these stoichiometry questions. And let's see if I can do any other question. Esther says, let me see all these other questions. Esther says, can you go over how to balance equations in an easy way, because I struggle on that, and the types of chemical reactions. My test is on Wednesday. Thank you. Sure. Okay. Let me see what I can do with that. Let me grab my questions of types of reactions, and then I'll show you how to balance overall types of reactions. Here we go. Okay. Let me actually find a better question, because I've done that a lot. And I do have several different videos also on balancing equations that I can see if I can link up to. Where are we? Let me find one more question for balancing equations. Where is it? Where is it? I don't want to do the same one on the video, so you can have that resource. Let's see if I can find anything. If not, I'll just make it up. I might just write a different one. Okay. Okay. Yeah, I'm just going to write a different one. That works. That works. Okay. So let's say if we have this equation, and I'll show you how to balance everything, a quick and easy way to just do this instead of having to deal with all of these oxygen here. Okay. Let's start here. So the first things first, whenever you have some sort of polyatomic atom, you don't want to separate it. Now, that's only going to be the case if they're both the same on either side. So meaning if we were to have NO3 on the reactant side and it's the same thing, it's the same exact thing on the product side, so NO3 here, then I'm not going to break that apart. And what I mean by that is when I'm writing all of my elements on either side, I'm going to leave it as NO3. I'm not going to break it apart into just nitrogen and oxygen. So I'm going to leave it intact when I can do that whenever they are the same on either side, as highlighted in blue here. So now I'll keep going and just write all of the different elements that we have and how many of each we have on either side and so on. And then that'll help us balance. So next, we'll look at nickel, and nickel only has 1. NO3, there are actually 3. So this subscript, anytime there's some sort of parentheses with the subscript on the bottom, like in this case, then that means there are 3 or however many numbers, whatever our subscript is. And then I'll kind of give you another reference here. Like if this were a 2, then there would be 2 NO3s. If, let's say, we had OH and this was a 2 again, then there would be 2. However, if this was just by itself NO3, then there's just 1. Since there is no other, there's no parentheses, there's no subscript there, we're not going to count that 3 on our oxygen. We're not counting this as 3 because that's already intact. That's part of the polyatomic atom already. Okay, so now I'm going to keep going, and potassium, or K, is going to be 1, and then Br is 1. Same thing now for the opposite side, just looking at how many of each. I have 1 for nickel. Our NO3 polyatomic is just 1 in this case, and then potassium is K, and bromine is 3 due to this subscript. Okay, so we aren't balanced just yet. We need to balance out our NO3 and our Br. So doesn't matter which one you decide to choose. I'm going to start off with the Br. Why not? It's just me choosing here. Okay. So now I'll put a 3 in front of KBr. We have to put it in front of the entire compound. And then what's essentially going to happen is this is going to distribute for both of our elements. Okay. So then I'll put 3 now for our K. And then now we have 3 bromine. And everything else stayed the exact same. And then, okay, we're no longer balanced even more a little bit because we still need to balance out K and NO3. So what do I have to place in front of that, in front of this? Well, this is going to be 3. And that's, again, going to distribute into both. And then our nickel didn't change. Our NO3, however, because of that 3, it made it 3. And then our K, or potassium, it also increased it to 3. And then bromine is 3. So boom, we're done. That's really what I want you to look at when it comes to balancing equations. I actually have multiple videos for balancing equations that I can see if I can link up. Yeah, so balancing equations, I believe I have 2. I have one with fractions and another with just balancing in general that I can link up in the chat right now. And yes, so I hope that helped, guys. I wanted to quickly note something else. Like, everybody who's kind of, asking me different questions, and I do see several, like, let's say, I see, like let's say, Norma, like, I see that you're asking for dispersion forces and hydrogen bonds. I just did a video on intermolecular forces that covers all of that in detail. So a lot of these things I do recommend, guys, checking out the videos that I do have, because I do have, and I don't know if you guys know about that. I do have a lot of balancing equations, a lot of metric system and unit conversions, stoichiometry. I just also uploaded ideal gas law. So that's definitely something else as a resource. Same with like molecular and empirical formulas. I have that resource already out for you guys. Just letting you guys know. I know I have several videos, so it's hard to find, but there's always a search feature on top for YouTube. So that's kind of something I'll be linking and putting as many links as I can see to answer these questions. I also wanted to let you know that if you came in a little bit later, thank you for coming. Thank you for being part of this Q&A. And overall, wanted to let you know what I'm working on, what I'm doing for you guys. I wish that I can do Q&As as much as possible. At this time, I can only make the Sunday times, but what I'm trying to do to kind of clone myself per se is I have designed these really detailed workshops. So what a workshop is, and specifically what it's tailored to right now, is the topic is Lewis structures. So I did a Lewis structure workshop that is ridiculously in detail. It comes from, how to know how many valence electrons something has, to how to draw a Lewis structure, how to figure out if it's polar, non-polar, it's hybridization, it's geometry, formal charges, resonance structures, and so on. It's a very, very detailed and awesome workshop that I highly recommend. I will be placing that after, it's actually on every single one of my videos, but I'll be placing that at the end. It's already in the description box of this live session. So that's something I recommend checking out. It is currently on pre-sale. What that means, it's half off right now. It is at a very, very low price. I want to make education as, affordable and just make it understand. Like, you could actually understand it. I know that chemistry can be so complicated. Trust me, I went through it myself. So I want to find a way to just help you guys and make it just crystal clear. So definitely recommend checking that out. I just placed the link in the chat box right now. It is a Lewis structure workshop, so definitely check that out. As I mentioned, it currently is on pre-sale. It also comes with my own notes that I've designed specifically for you guys. Think of it as kind of like the how-to guide to Lewis structures, to drawing Lewis structures, and everything that you need to know that go along with Lewis structures. I also just made my own like study guides and notes that I'm also creating. That's what I've been working on top of the videos and everything else and workshops that I do for you guys. So the study guides, I'll also be placing that in the description box as well. And I just placed that in the link too. So I made two different study guides, one for Lewis structures and the other for limiting reactants. So if you had any trouble with limiting reactants, excess reactant, percent yield, theoretical yield, actual yield, pretty much absolutely everything that you need to know with limiting reactants, I highly recommend checking that out. It's at a very, very low price point. And think of it as it's even cheaper than your own Starbucks drink. So as I mentioned, I really wanted to make, this something that you guys could easily get. And yeah, so that's what I've been working on. This week, I will be launching another video on YouTube. So definitely check that out. And of course, if you did get your question answered, as you can tell, I do get several questions throughout this hour. I do this every single Sunday. For those of you who are new to the Q&A, every single Sunday at 12 p.m. Pacific time. I'm in California, so it's different timing. So I recommend coming early. I typically start the live 5 minutes early. I let you guys, I keep you guys updated as to what's happening. And Shelly just saw, oh my gosh, it is cheap. Yeah, Shelly, I've made it very, very affordable. Like I said, I want you guys to succeed. Like ultimately, that's something that I'm passionate about and my heart is in it, because I wish someone was there for me personally. When I went through this, I got more naysayers and people that were kind of telling me to give up than I had, cheerleaders. So I then wanted to become that for you guys, because we need that in the world. So especially in the education world, and especially in, these tough concepts that you feel like, am I smart enough? Am I really capable of doing this? And yes, you are. And most people tell you that you're not. So that's why I provided all of these different resources and just trying to give you all the knowledge that I've, figured out over the years, and shortening that learning curve so you don't have to make the same mistakes that I did, and that you can just succeed overall. I wish someone can just tell you that, so I became that person. And to continue on with my other statements, sorry. So every single Sunday I do this. I definitely recommend coming early. Like I said, it's 12 o'clock p.m. Pacific time. So definitely figure out what time that is for you guys, whatever state or place you're in. And I highly, highly recommend coming with an exact question, just to make sure like we can move this along like super fast, or I wouldn't say super fast, but I'm trying to answer all the questions thoroughly and all the questions that I can in an hour. So yeah, at this time, I'm doing this every single Sunday. Sadly, I can't do this every single day. I also do have another job where I do tutor students, so that's something separate. So yeah, that concludes today's Q&A. Thank you so much for being here, and I hope to see you guys next Sunday. And definitely after this video, after this live, I'll be placing a timestamp, just meaning the questions that were asked and when I answered them. So if you need to go back, maybe you forgot what I stated, or you want to see what other questions were asked today, definitely check that out. I've been doing that for every single live session, my previous live sessions. So I recommend a look at that. Some of these questions can definitely benefit you to see, maybe you might have the same exact question. Most people do. So check that out, and I'll see you guys Sunday. See you guys.